Welcome to the lecture series session on EST 130 Basis of Electrical and Electronics Engineering. My dear students, today we are going to discuss about the Zener diode and its characteristics. And we have discussed about the PN junction diode characteristics. Zener diode is also a PN junction diode only, but it has got its own characteristic features while it is used in a circuit. We know that Zener diode is having the breakdown of the junction occurring on field ionization method or field ionization manner. So that particular junction, breaking of the junction is called field ionization. Or Zener diode has got a Zener region. On that Zener region, the field ionization is actually causing to break down the junction. And that is why this Zener diode can be used in circuits in the reverse biased condition. Usually, the Zener diode is having PN junction and it has got forward and reverse characteristics. But usually, when we use Zener diode in circuits, we use it in the reverse biased manner. Or the reverse biased characteristic of the Zener diode is actually used for making it as making it as a device for using in some voltage regulation purposes and all. Okay, so that we will come across each one of the characteristics here. So first, what is a Zener diode? Zener diode is a reverse biased heavily doped PN junction diode which operates in reverse breakdown region. Zener diode is a two-terminal cathode and anode. And here, the thing you have to understand is the Zener diode is having a heavily doped PN junction and with a very thin depletion region. It has got a very heavily doped PN region and it has a very thin depletion region. So PN diode is, PN diode we have seen, the case of PN diode it is slightly appreciably big or thick depletion region, isn't it? When it is reverse biased. Here the Zener diode is connected in a reverse biased condition in a circuit. When applied voltage exceeds, that is the main peculiarity of this kind of diode. The breakdown of the diode junction occurs when it is reverse biased condition and the diode is in operation. Breakdown means does not permanently break down the junction and damaging the diode. No. The Zener region, if it is operating, means the diode can be operated in breakdown region for satisfactory application purpose. That is the idea. When applied voltage exceeds the breakdown voltage, Zener breakdown occurs. And this kind of breakdown is called the Zener breakdown. So a sharp increase in current with the voltage across the diode which remains constant while Zener breakdown occurs. When the Zener breakdown occurs for a reverse biased Zener diode, what happens? A very large reverse current will be flowing through the diode junction with the voltage across the junction made constant. Or once the reverse biased PN junction of the Zener diode is break down or broken down, what happens? The reverse current will be very large. So that will be very large and that will be flowing very large at the same time, which keeps a constant voltage across the PN junction of the Zener diode under reverse bias. And that voltage is almost constant. Once the Zener breakdown occurs, the voltage across the Zener diode will be almost constant. That is the main feature of this particular diode. The Zener effect is usually occurring for a voltages less than 6 volt or less. Usually, the Zener effect or the field ionization is occurring when the voltage applied across a dielectric or a depletion region like dielectric or depletion region having very high resistance. And if that particular region is applied with a voltage of 6 volt or less, or in other words, if that particular junction is reverse bias junction is applied with 3 into 10 raised to 5 volt per centimeter or 3 into 10 raised to 7 volt per meter, then in such cases, since it is a thin junction and also heavily doped, this heavily doped thin junction, when you apply a voltage, that gives sufficient field intensity, electric field intensity. This electric field intensity causes to break down the covalent bonds of the crystal of the material. So, Zener diode material, which is essentially a silicon or germanium, whatever, since it is heavily doped and thin junction, and that thin junction is subjected to a heavy electric field intensity that might cause to dislodge the covalent bonds of the crystal structure at the junction. When the covalent bonds are broken, what happens? A very large number of electrons will be getting free, and these electrons will be trying to reach to the conduction band, because once the covalent bond is broken means this electrons will be getting freed, and that will become a valence electron that will try to, some of the electrons will be trying to recombine with the holes there, and the remaining electrons will be going to the conduction band as a conduction band electrons, right? So this kind of ionization and this kind of breaking of junction is called field ionization, and this field ionization is the main reason for breaking down the junction of a Zener diode. Okay, and that is usually taking place in the Zener junction at a voltage intensity or electrical field intensity of 3 into 10 raised to 7 volt per meter or 3 into 10 raised to 5 volt per centimeter. And that occurs when a voltage of 6 volt or less DC voltage, when a DC voltage of 6 volt or less is applied across the junction under reverse bias junction. Okay, so this is the symbolic representation for the Zener diode. You can apply, you can symbolically represent it like this. This is the anode and this is the cathode, and here it can be represented like this also. Both are correct. The arrowhead in the symbol points towards the conventional direction of current. This is the arrow symbol, that is the conventional current flow through the Zener diode. Now, how the Zener diode works? When a reverse voltage that is 6 volt or less is applied to a Zener diode, it causes a strong field appears across the narrow depletion region. I told you already, across when the PN junction is reverse biased, depletion region will be developed here. And here in the case of Zener diode, the depletion region is very narrow and also it is a heavily doped PN junction. Then what happens? The field intensity of the order of 3 into 10 raised to 7 volt per centimeter is developed across the junction, and that exerts a force on the electrons in the outermost shell. What is the outermost shell? That is the valence electron. And that electrons will be exerted. So that electrons are exerted with a very high field intensity force or very high electric force, and that causes to dislodge the electrons in the outermost shell. Since the Zener diode is heavily doped, this electric field is strong enough to pull some of the valence electrons into conduction by breaking their covalent bonds. I just told you now how this process is taking place. Once the covalent bond is broken, the electrons are getting freed, and some of the electrons will be trying to recombine with the holes there, but the most of the electrons which is getting freed will be coming to the conduction band, constituting a current. And this process is what is called the field ionization or Zener breakdown. This is what is called the Zener breakdown or field ionization. So the breaking down of the junction of a Zener diode under reverse biased condition is mainly due to the field ionization. Okay, large number of electron hole pairs are generated due to the strong field developed due to the reverse bias. Large number of such free electrons will constitute a very large current in the reverse direction or reverse current. That is a very large reverse current because it is a reverse biased PN junction, isn't it? Zener diode is under reverse biased condition only. So the current flowing through the junction is the reverse current. Or we say that the current flowing through the junction under breakdown or Zener condition or Zener breakdown is what is called the Zener current. That is the Zener current. Or Zener diode is the diode is said to have occurred the breakdown, Zener breakdown, or this is what is called the Zener effect. This kind of breakdown of the junction due to the reverse biased condition with the application of a voltage across the reverse biased junction is called the field ionization, and the junction is said to occur Zener breakdown, or that is what is called the Zener effect. Usually, in order to limit the current, we have to connect a current limiting resistor in series with the Zener diode. Otherwise, what happens if the current is increased more and more? The junctions will be getting heated up, and there is a stage at which the current, reverse current, will be getting more, and the junction will be heated up more and more, and finally, a permanent damage of the junction may occur due to that. That should not happen. That's why a current limiting resistor is always connected in series with the Zener diode. Okay. Now, what is the VI characteristic of Zener diode? Just very similar to the ordinary PN junction diode, we have forward characteristic and reverse characteristic of the Zener diode has no implications, direct implications for any kind of practical applications, because it is very similar to a PN junction diode characteristic. The forward characteristic of a Zener diode is very similar to that of a PN junction forward characteristic. But the reverse characteristic, that is reverse characteristic of the, or the reverse biased condition, the PN junction under reverse biased condition is of importance, and that particular characteristic is of importance to understand, because the Zener diode is usually connected in the circuit in the reverse biased condition. So when the diode is forward biased, it behaves just like a PN junction diode. Initially, for small values of applied voltage, diode does not conduct, and hence there is negligible current. But when the diode voltage in the forward biased condition increases cut-in voltage or new voltage, current increases with increase in voltage as shown in the figure here. This is the forward voltage that is very similar to forward. This is the forward voltage, which is very similar to the curve of the PN junction diode. But for a Zener diode, we are much interested to have the reverse biased condition or reverse characteristic. This is the reverse characteristic. So we will see the reverse characteristic. The anode of the Zener diode is connected to the negative terminal of the potential source, and cathode is connected to the positive terminal of the potential source. Then we said that the diode is said to be a reverse biased diode. And in practice, the Zener diodes are used in circuits in the reverse biased condition, or that diode is used for such applications only. So reverse characteristic, that is VI characteristic of the reverse biased Zener diode, is shown here now. We have seen this is the reverse characteristic of Zener diode under reverse biased condition. You are applying a reverse voltage, and that reverse voltage, initially the current is very small. Here the current is of the order of milliampere, but here the current is of the order of microampere initially. But after the Zener breakdown occurs, after this breakdown voltage, here this is the breakdown voltage Vz. The Zener breakdown voltage is usually designated as Vz, V suffix Z. So after this breakdown, the current increases very sharply like this. See, with a very small increase in current, a very sharp increase in, with a very small increase in voltage, a very sharp increase in current occurs here. Or we say that after the breakdown region, the reverse biasing has not any direct relationship with the reverse current. Or in other words, the reverse current increases very sharply, keeping a constant voltage across the reverse biased PN junction Zener diode. Across the Zener diode, after the breakdown, the voltage across the Zener will be, for Zener diode will be constant. See here, this curve is almost like this parallel to y-axis. So the voltage across the Zener diode will be almost constant after the breakdown. But for satisfactory operation of the Zener diode, there will be a minimum value for the breakdown current or Zener current, and there will be a maximum value for Zener current. Between these values, if the Zener diode is operated, the Zener breakdown will never occur any permanent damage for the diode. If the current is increased more than this IZ maximum value, A very severe current will cause to make more and more heat dissipate at the reverse bias PN junction. That heat may cause to damage the reverse bias PN junction permanently. That is why we always fix a minimum value for the breakdown current, that is Zener current, and a maximum value for the Zener current. So after the breakdown occurs, the voltage across the Zener diode will be almost constant, or we can say that practically it is constant. Okay, right? So that is why the Zener diode is designed to operate in reverse bias condition. For small values of reverse voltage, the reverse saturation current is negligibly small. That we have seen. We have seen here. For small value of reverse voltage, so when the reverse voltage is this much, this is the voltage axis, and this is the voltage axis, and this is the current axis. This is the voltage axis. For smaller values of voltages, of course, the reverse current is very small. But when the voltage is increased after a certain value, V is suddenly the current increases. That is what is mentioned here. For small values of reverse voltage, reverse saturation current is negligibly small. As this current flows due to the thermally generated minority carriers, because it's a reverse bias junction. Anyway, when you give a very small reverse voltage, of course, say reverse bias junction. In the reverse bias junction, initially the reverse saturation current will be due to the thermally generated minority carriers, right? But after a certain value of the reverse voltage, the reverse current increases suddenly and sharp. This voltage is called the Zener breakdown voltage VZ, as shown in the graph that we have seen. Now, the value of VZ can be precisely controlled by controlling the doping levels of PN junction. The VZ can be designed by properly controlling the doping level of the PN junction, because PN junction is a reverse bias junction having heavily doped. So the doping can be controlled. And with this controlling of the doping, the VZ can also be controlled. Okay. And this VZ has got direct impact upon the temperature rise. With increased temperature, VZ can be increased in the case of a Zener diode. Okay. Once the Zener breakdown happens at breakdown voltage, the voltage across the diode remains constantly equal to VZ and current increases faster voltage. Any increase in the source voltage will result in increase in current, reverse current. Any increase in, of course, the voltage, if you try to increase, that will increase the reverse Zener current. But the if you try to increase the voltage, of course, the voltage across the Zener will be constant. It will be made constant. But the current will be increased because you are applying more source voltage on the reverse bias condition. The reverse current through the Zener diode should be limited by connecting a series resistor to avoid the damage of the device due to excessive heating. The reverse current through Zener diode should lie between a minimum and a maximum value. I just told you what is the IZ minimum and IZ maximum in order to safely operate the device in the reverse bias condition. Okay. What are all the applications of Zener diode? After the breakdown, the Zener diode operates in a region called the Zener region. Once the breakdown is occurring in the the Zener diode is now operated in the Zener region. Doesn't mean that the Zener diode has been damaged totally. No. The diode will be operating in the Zener region, and this particular characteristic of the Zener diode can be used for regulating the output voltage of regulators. How is it done? That we can just see now. So, in the Zener region, the voltage across the Zener diode remains constant. That is the main behavior of the Zener diode. Once the Zener diode breaks down the region due to its reverse biasing, reverse biased operation, its voltage across the Zener will be constant. But the current changes depending upon the supply voltage. If the supply voltage is increased, of course, the current will be increasing. The operation of the diode on the Zener region is being used for voltage regulation purposes. So the Zener diode can be used as a voltage regulator. And it can be used as a peak clipper in wave shaping circuit. In order to wave shape, for shaping the waveform of certain circuits, you can use it as a peak clipper. Clipping means that is shaping, clipping the waveform. In such circuits, you can use it as a clipper, and which can be used for meter protection against damage from accidental application of excessive voltage. For analog instruments and other digital instruments also, for meter protection, for the protection of the meter itself, is done with the help of a regulation mechanism. In that regulatory mechanism, a Zener diode is used as the voltage regulator to give voltage to the instrument. So it can be used as a meter protection unit against the damage of a or accidental damage of an instrument. Now, how Zener diode can be used as a voltage regulator? That's what we are going to discuss. A Zener diode can be used as a voltage regulator to provide a constant voltage from a source whose voltage may vary over sufficient voltage. Now, let us consider a circuit with a load resistor RL. Here we have a load resistor RL. This is the load resistor RL, and this RL across which the Zener diode is connected. The load resistor RL is having an output voltage of E0 here with an input voltage of EI here, and this voltage may be from a power supply, DC power supply, which is unregulated. And once this regulator is also connected here, you will be getting the output at these two terminals of the load. Load may be anything, resistive or whatever, whether it is a meter or circuit or anything, that will be connected between these waves. That is the lead of the output of the regulator, voltage regulator. And here this R, which is connected in series with the circuit, is the current limiting. Now, if the circuit is properly designed, the load voltage E0 remains constant. If you design the circuit in such a manner that the Zener diode operates its Zener region properly, then across the Zener diode, the voltage will be constant, or the voltage, Zener voltage Vz will be equal to the output voltage available across the load resistor RL, that is equal to 0. So Vz is equal to 0. Okay, and that can be made constant because once the Zener diode is operated in the Zener region, this voltage will be always operated. So we can just consider two cases: whether the input voltage is increased or load current is increased. These two cases are usually occurring in any voltage regulation circuit. Now, suppose your output of the rectifier, that after smoothing is connected here. Now, the output of the rectifier is connected here, that has to be regulated, or that is connected as the input to the circuit. EI is the input voltage. Suppose this EI is gradually increased. So such an increase will cause to increase the load current I. This is the total current I. What is I? I is the sum of IZ and IL, isn't it? IZ and IL. And this is positive and this is negative. The current is flowing like this, isn't it? The current is flowing like this. This is positive, this is negative. So current is flowing like this. Right? So this is negative and this is positive for the Zener diode. So it is reverse biased. Should be connected. If you put plus positive here, then this is to be reverted like this. Follow my point. So now this is reverse bias, and let us consider the case that there is a tendency to increase the input voltage, but the output voltage must be E0, that is to be made constant. How this voltage regulator can do? If the input voltage is increased, I will increase, isn't it? The total current I will be, that is the load current, and IZ will be increased. And that will drop a voltage here, that is IR drop. And when that particular voltage drop is here due to the increase of load current, due to the increase of input voltage, not load current. Input, we are considering the input voltage is increased. When the input voltage is increased, the load voltage will not be any variation, will not be having any variation. It has to be kept E0, that is constant. Or if E0 is constant, IL must be constant because the voltage RL is not varying, RL is constant. We consider that only input voltage is varied. The load resistance is fixed, RL, and that has got a voltage E0 that has to be kept a output voltage of E0 connected to this load. So E0 by RL is kept constant, that is equal to IL. If that is the case, if the input voltage is increased, when I is increased, that what happens? This voltage regulator Zener diode or the Zener diode should operate on its inner region. Or in other words, since this Zener diode is connected in the reverse biased condition, it operates in the Zener region. Once it operates in the Zener region, the current through the Zener diode, that is the Zener current, will be increased with the increase of input voltage. Why the Zener current is increased? Because the load current cannot be increased because load voltage is kept E0, that is to be made constant. So once load current is made constant, load voltage is made constant means load current will be constant because RL is not changing. So IL cannot be changed. IL is IL only. Only change may occur is to increase IZ. That happens when the Zener diode is operating in the Zener region, when the input voltage EI is increased. So that increased IZ and IL will constitute the I to be increased, and that will drop here, and that drop will maintain the E0 to be constant. That is numerically equal to Vz. Or in other words, when the input voltage is increased, the output voltage is kept constant without having any change. It is kept constant as E0, that is equal to Vz. In this way, the Zener voltage regulates the input voltage, regulates the variations in input voltage and getting an output voltage that is constant in the output. So in that case, we can consider this Zener regulator or the Zener diode to be a voltage source having Vz as its voltage. Very similar to here, a battery which is connected as Vz in this manner. Just a comparison, that's all. Because after the Zener diode is broken down, that is Zener breakdown occurs. Once the Zener breakdown occurs, the output or the voltage across the Zener will be its Zener voltage, that is Vz, that is constant, and that is numerically equal to E0. That is why the circuit can be considered to be a voltage source Vz with all the circuit parameters connected here, like this. Follow my point. So in this way, the variations in input voltage is regulated by this regulator in order to maintain the constant V0, that is the load voltage at the load R. Okay. Now suppose the load resistance is increased or decreased. That may happen. The EA is not having any change. EA is as it is. There is no change in EA. EA is as it is. There is no change. There may have load changes occurring on the load source. RL may be varied. When RL is varied, what happens if the voltage E0 is EA is constant, so E0 will be always there, is made constant. But when E0 is constant and RL is varying slightly due to some cases, if you add more circuit resistance, then it will be having a slightly increased RL. Sometimes if some of the circuit resistance is gone, not resistance alone, there may be so many other circuits and some resistance has been taken out. Then again the resistive load or the load resistance will be getting decreased. So when the load resistance is getting decreased or increased, since E0 is kept constant, IL will be increasing or decreasing, isn't it? IL will be increasing or decreasing. This IL increase will be causing to increase I, isn't it? But what about IZ? In order to, because here there is a tendency to increase I, but you have to see that the load cannot take the additional load current from I, or I cannot be changed. Only change due to the increase in IL can be substituted only with this IZ. Or in other words, in order to maintain the same I, because A is not varying, in order to maintain this I, though IL is increased, I has a tendency to increase, but it should always maintain the earlier value, constant value. How is it possible? The Zener will be decreasing the Zener current when a load resistance variation is occurring, or when there is a change in load current. Whenever there is a change in load current, the Zener will have a tendency to decrease the Zener current in order to compensate this increase in load current, so that I will be made constant, so that IR will be always constant, that maintains the voltage E0 constant. Okay, so in either case, that is whether input voltage is increased or decreased, output is made constant, output voltage is made constant. When the load current is increased or decreased due to the variations in load, again the output voltage E0 is kept constant equal to Vz. So in this way, the Zener diode can be the voltage at the output side of the regulator to be constant. Okay, this is the voltage regulator, and this is how the voltage regulation is done with the help of a diode regulator, and how this components can be increased or the components can be designed. That is here. Suppose if you want to know the current limiting resistor, value of the current limiting resistor, we know what is EI, that is the input voltage we can measure. The output voltage also we have designed, and that is the. So EI minus E0 is the voltage drop that has to be dropped in on this one, IR, isn't it? So, but what is I? I is equal to numerically equal to the Zener current I, Z and IL, sum of these two currents. So, since I is known to you due to these two currents, you can find out the value of the current limiting resistor R by applying the equation, the variations in voltage, that is EI minus E0 divided by I Z. And you can see that Vz is equal to E0. So, the load current IL is equal to V by E0 by RL or Vz by. So in this way, you can find out these component values. Okay. So with this, I think we can conclude here today's session, and I'm very thankful to you, all of you, here for patiently hearing my lecture session here. Thank you very much. Wish you all good luck for the coming examinations and the preparation for the examinations. Okay.